Hello, everyone. This is Ashley Childress with the Statistics Division of ASQ. I would like to welcome you today and thank you for joining us. Our speaker today is Dr. Jack Revelle, a consulting statistician with Revelle Solutions, LLC. Jack has a BS in Chemical Engineering from Purdue University and an MS and PhD in Industrial Engineering and Management from Oklahoma State University. He is a fellow of the American Society for Quality, the Institute of Industrial Engineers, and the Institute for the Advancement of Engineering. Dr. Revelle is the recipient of many notable awards, including the ASQ of Los Angeles Simon Collier Quality Award, the ASQ Dorian Chanin Medal, the Distinguished Economics Development Programs Award from the Society of Manufacturing Engineers, and the Distinguished Faculty Award from the National Graduate School of Quality Management. He is one of only 2 persons in the world who has been honored to receive both the Taguchi Recognition Award from the American Supplier Institute for his successful application of robust designs and the Akal Prize from the Quality Function Deployment Institute for his outstanding contribution to the advancement of QFD. The title of today's webinar is Process Capability Analysis using CP and CPK Indices. All phones and microphones other than the presenters have been muted. So if you have any questions or comments during the webinar, please use the questions interface in your GoToWebinar control panel. I'll hold these questions until we take a break for questions. So at this time, I'm going to hand things over to you, Jack. Thank you again for presenting with us today.
It's my pleasure, Ashley, and I'm ready to go, and I hope everybody else is. Let me reiterate what you just mentioned about the fact there will be at least 1, maybe 2 breaks, at which time I'll ask Ashley if there's any questions that have been called in that I will attempt to address. So let's go. I think everybody can see the screen now.
Yes, we can.
And the title, as we mentioned earlier, is Process Capability Analysis using C sub P and C sub PK indices. And you've already mentioned about my background. In case anybody's interested, I'm located in Orange, California, about a 15-minute drive from Disneyland, and so I tend to have a kind of a California Disney approach to statistics. But let's go ahead. Here's our agenda for today. We'll start out with a brief discussion of the normal distribution. I'll assume that everybody that's online today has a relatively simple background with relationships distribution, probably having had 1 or 2 or more courses in statistics during their college career. Then we'll get into some relevant definitions. I'll give you a pretty good example of what this looks like. We'll talk about the interrelationships that exist between C sub P and C sub PK. Then we'll talk about process yield and the infamous plus or minus 1.5 sigma shift, followed by a look at process measures, some 6 sigma equivalencies, and finally a summary. So with that in mind, we'll go ahead and get started. And here's the well-known normal distribution, also known as the bell curve. Over on the right is a graphic of the normal distribution, and on the left is a verbal summary of the normal distribution. Part A, which is in the center of the normal distribution on the right, has 68.27%, approximately 2/3 of the population that the bell curve is measuring exists between -1 and +1 sigma, representing 34% on the left side of the mean and 34% on the right side of the mean, for about 68.27%. Part B, which includes Part A, represents ±2 standard deviations. And in addition to the original 68.27%, we have an additional 13.59% on either side of the mean. And so that results in 95.45% of the population, virtually 100%. But we get even closer to that when we go to Part C, which includes Parts A and B. And now what we've got is 99.73% of the population, which exists between ±3 standard deviations. Now, those plus or minus 3 standard deviations represent what we call in statistical quality control or statistical process control, the lower control limit at minus 3 sigma and the upper control limit at plus 3 sigma. Therefore, outside of plus or minus 3 sigma, we have 0.27% of the area under the curve. That's 1/4 of 1% of the population or the sample exists outside the plus or minus 3 sigma limits. And where we get the 0.27%, of course, is 100%, which is the entire area under the curve, less the 99.73% that represents part C, and that is the within the upper and lower control limits of the curve. So that's a very quick overview of the quantitative aspects of the normal distribution curve. Now move on with some definitions. The USL and LSL are what we call the upper and lower specification limits. The specifications being having to do with a part or a process or whatever it may be that's set by management, set by engineering, whoever has the legal authority to say what is the acceptable upper and lower limits of the specifications of the entity that we're looking at. And then, of course, we have the UCL and LCL, which is the upper and lower control limits. Now, I just discussed that on the previous slide. That's the plus or minus 3 standard deviations from the center of the process. Then we come to DSW, the design specification width, which is the upper spec limit less the lower spec limit. And so that is those are the boundaries of the what's acceptable in this particular process or this particular product or entity. And so we have the DSW, design specification width, which is the upper and lower spec limit difference. Finally, on this page, page 5, we have the natural process range. That's the upper control limit less the lower control limit. And that's what we would expect with a normal distribution, is the range, the plus or minus 3 sigma of the normal distribution curve. And we'll be dealing with the design specification width and the natural process range as we move on through the example. Let's continue now with the definitions. First, we have the lowercase Greek letter sigma, which is the process population standard deviation. And then its equivalent for a sample, the lowercase s, as in the alphabet. So we have sigma for the population and s for the sample for the standard deviation, whether we're dealing with a product, a process, or whatever it may be. The third item on page 6 is X double bar. People who know me well remember that I used to have a ranch down in Arizona called the X bar and R ranch. Drove my neighbors crazy. At any rate, X double bar represents the process average when you're dealing with a sample. And then finally on page 6 we have the capital Z, which is the distance between the process average and either the upper or lower spec limit. It's measured as the number of standard deviations. Like if we start at the process average or the nominal, what we've got is the distance measured in standard deviations, like 1.96 sigma or 2 sigma, whatever it might be, as we move to the right or left of center. Moving on to page 7, continuing with our definitions, we have C sub P, which is known as the process capability index. This estimates the extent of process capability if a process is centered, but without respect to the spec limits. This is talking strictly about the process capability of the process. It assumes the process output is approximately normally distributed. Now, if there's some concern about whether or not it's approximately normally distributed, there are tests that can be run to evaluate the distribution to see if it's normally distributed. At any rate, this process capability is the design specification with DSW that we spoke of earlier, divided by the natural process range, the NPR, both expressed in terms of sigma. So C sub P, let's review this page. C sub P is the extent of the process capability if the process is centered without respect to the spec limits, and it assumes normality in the distribution. And C sub P, in terms of a quantitative statement, is the design specification width divided by the process range. That's the upper spec limit minus the lower spec limit expressed in standard deviation units divided by the natural process range, NPR, which is the difference between the upper and lower control limits, again expressed in terms of the standard deviation. Now let's move on to page 8. Continuing with definitions again, C sub P, as I just mentioned, is in the numerator of the ratio, we have the upper spec limit minus the lower spec limit. That's the numerator. The denominator, the upper control limit minus the lower control limit. Both the numerator and denominator expressed in terms of sigma units. So C sub P then is equal to X sigma divided by 6 sigma. 6 sigma, remember, is the natural process range in the denominator of the definition of C sub P. X sigma, as you can see, is the design specification width. That's the numerator, the upper spec limit minus the lower spec limit, divided by the value of the standard deviation. Where the objective is that C sub P, the process capability index, should be greater than or equal to 1. When it gets less than 1, you've got defects built into your process or into the products that are being produced. Moving on. Here we have the design specification width expressed graphically. In the center, you can see we have the natural process range, the NPR, which is 6 sigma, starting in the center and moving to the right and left, plus or minus 1 sigma, representing about 68% of the area under the curve, plus or minus 2 sigma, representing about 95%, and plus or minus 3 sigma, representing 99.73%. That distance from the minus 3 sigma to the plus 3 sigma, or vice versa if you prefer, is the lower control limit to the upper control limit and represents 99.73% of the area under the curve. That leaves in the shaded tails or skirts at either end of the curve a 0.135% that naturally falls outside of the upper and lower control limits. And furthermore, in red, you can see the upper and lower spec limits. Now, I've arbitrarily put those limits there. They can be closer to the center of the process, or they can be further from the center of the process. And the further they are from the center of the process, the fewer defects that are going to be experienced. So what we've got is C sub P, which is equal to, at the top of this graphic, the design specification width divided by, in the denominator, the natural process range. Continuing with our definitions, we have C sub PK, which is a version of the process capability index entitled the mean sensitive process capability index. This index is an adjustment of C sub P to account for the effect of non-centered distributions. Remember, C sub P made the assumption, rightly or wrongly, that a process or product that's being evaluated is centered. In this case, the C sub PK is a measure that is being used to determine whether or not we have a capable process or product with a non-centered distribution. So C sub PK is then the quantitatively stated location of the natural process range. That's the location of the upper to the lower control limits with respect to the boundaries of the design spec width. When the process is centered on the nominal or target specification, C sub PK is always equal to C sub P. That means the mean sensitive process capability index is equal to the process capability index. That's the only time it happens, is when the process is centered on the nominal spec limit. Otherwise, C sub PK is less than or equal to C sub P. That should really be C sub PK is less than, not less than or equal to C sub P. My error. Sorry about that. And it assumes the process capability is approximately normally distributed. Okay, here's our definitions. C sub PK, the location sensitive, is equal to Z. Remember that's the number of standard deviations from the mean or target. Z minimum divided by 3. Now we have two Z minimums. Z upper, which is to the right of the mean, and Z lower, which is to the left of the mean. So Z upper is as you're approaching plus 3 sigma. Z lower as you're approaching minus 3 sigma. An easier way, perhaps, to understand that is that the location-sensitive process capability index is equal to the minimum value of either of two values, and that is on the left, inside the brackets, on the left, the upper spec limit minus X double bar, the processor product average, divided by 3 sigma, or X double bar minus the lower spec limit divided by 3 sigma. Whichever of those two is the minimum will become C sub PK. And we're hoping that C sub PK will always be greater than or equal to 1. That is to say, the objective is C sub PK should be greater than or equal to 1. Now, before I get into the example, Ashley, you want to check and see if anybody has any questions so far about the definitions?
Right now, we don't have any questions.
Obviously, I've either spoken too fast or I've made it so perfectly clear that everybody will remember this forever and ever.
Let's go with the form, or the latter, rather.
Okay. Okay. Well, let's start with the example then. And by the way, you notice that we're now on slide number 12, and there's a total of, I believe, 27 slides. Let's assume here that we are given a design for a product or a process, whatever it might be, that the design specification is equal to 100 plus or minus 6, where 100 is some unit. It may be feet, it may be degrees, it may be time units like seconds, whatever it might be. But the design spec is 100 plus or minus 6. Thus, the norm is 100. That's the center of the normal distribution, or we're assuming a normal distribution. The upper spec limit is going to be 100 plus 6, which is 106. And the lower spec limit is going to be 94. That's 100 minus 6. So the natural process parameters, X double bar, then the mean, and sigma, standard deviation, for a distribution assumed to be normal will now be varied for purposes of demonstration using the numbers 100 plus or minus 6. So on slide 13, we're going to first find C sub P, the process capability index. Our job is to calculate X double bar, the mean, and sigma. We'll start out with X double bar equal to 100, because that's part of our given from the previous slide, and the standard deviation equal to 2 for purposes of demonstration. So first we say C sub P is equal to the upper spec limit minus the lower spec limit divided by sigma in the numerator, divided by 6 in the denominator, and that's the natural process range. And we've already said that the upper spec limit in this particular demonstration example is 106, and the lower spec limit is 94. And the difference between those two, of course, is 12, divided by the value of the standard deviation, which is 2. And 12 divided by 2 is 6. And in the denominator, we already have 6. So in the last line, we have 6 divided by 6. And that tells us that C sub P is equal to 1. So we've got that calculation out of the way. Now, continuing with our example on slide 14, we're going to calculate C sub PK. Recall that the C sub PK in the way of its mathematical model or formula, is equal to the minimum value of either of two fractions. The one on the left within the brackets is the upper spec limit minus x double bar, all divided by 3 sigma. And the other ratio to the right, on the right side of the brackets, is x double bar, again the average, minus the lower spec limit, all divided by 3 sigma. Now in the final line on slide 14, we're putting some numbers in there, and we see the upper spec limit is 106, and the x double bar, which we were given originally, is 100, and that's 106 minus 100 is 6, and in the denominator of that particular fraction, 3 times the standard deviation, which is 2, is also 6. So what we've got on the in the left-hand ratio is 6 divided by 6, and over on the right side, we have x double bar minus the lower spec limit, which is 100 minus 94, which is 6, divided by 3 times 2, which is 6. And so what we've got is that each of these two, and I'm moving to the next slide now, each of these two ratios are equal. That is the minimum of the two different fractions. They happen to be exactly the same, and so we know that C sub pk is equal to 1, because we're going to take the minimum value of either of those two ratios. And in the last bullet on slide 15, we can see then that the C sub pk is equal to C sub p. So the mean sensitive process capability index is equal to the process capability index. Thus, it can be safely concluded that the process average x double bar is centered on the nominal specification. Okay? What's our conclusion? On slide 16, since C sub p is greater than or equal to 1, we conclude that the process is capable of producing work within the specifications. Since C sub pk is also greater than or equal to 1, we conclude the work produced by the example process fits within the specs. And as a caveat at the end, even if C sub p, the process capability index, is greater than or equal to 1, remember that C sub pk must also be greater than or equal to 1 to be certain that a capable process is producing acceptable work. Acceptable work meaning that the process or the product fits within the given engineering or management specifications. Now, let's see what that looks like graphically. This is one of my favorite graphs. I developed this particular graph, golly, had to be in the mid-1980s. And the sound you heard was just me taking a little water. In the upper half of this particular page, or slide 17, we've got a C sub p of 1 with a standard deviation of 2. You see that up in the upper left-hand corner of that upper rectangle. Below that, in the lower rectangle, we have a C sub p equal to 2, and the standard deviation is equal to 1. Now let's take a look at the top half of this graphic. Starting on the left-hand side, we see we've got a nominal specification of 100 and upper and lower specifications of 106 and 94. Those values are over on the far right-hand side of those lines. So we see upper spec limit of 106, lower spec limit of 94. The nominal is 100. And when we've got a C sub p of 1, when the process is centered, it's going to look like that normal distribution curve on its side that you see on the far left-hand side of that upper graphic. But what happens when the process operators let the process slide a little bit? Maybe it's getting too big. And say what happens, suppose X double bar goes to 103 instead of being 100. Well, what happens, you can see that one of the tails, the upper tail specifically, is now producing defective product. And in this case, the calculation would have given us a C sub pk of 0.5, which is an immediate clue, a warning, if you will, that the process is no longer centered as it was on the far left. And so we do our research and we see we can calculate what the percent defective is in that particular state of the process. Moving further to the right, this is the second distribution from the right. We've let x double bar go to 106, and now the nominal, excuse me, the mean is now 106, which is coincident with the upper spec limit. That means half of the product is being produced outside the upper spec limit, and that is volumes, absolute volumes of defective product. The C sub pk in this particular case happens to be 0, and that is a mighty clue warning that the process has slid so badly that we're now producing 50% of our product is being produced in a defective manner. And as it goes further to the right, where we now got x double bar as 109, well, what we've got is just about most of the product is being produced defectively, and the C sub pk, as you can see, can go negative. C sub pk in this particular case is minus 0.5. And if the process operators and the supervisors and the managers aren't doing something, they need to be replaced. Now, let's take a look at the same process, but with a standard deviation of 1 instead of a standard deviation of 2. And this is the bottom graphic in slide 17. And what you can see is over on the far left-hand side, what we have is this with a C sub pk of 2, because the standard deviation is now 1, what we've got is the process is dead center, and we've got tons of room above and below that particular product, and so we can actually let the process deteriorate to the same extent that we let it deteriorate on the upper graphic. So what we've got an x double bar of 103. As you can see, neither tail is outside the spec limit, and so we're still producing virtually 100% defect-free product. Now, the C sub pk is 1. Remember, the C sub p is 2, and when the sigma is equal to 1, the standard deviation is 1, we have a C sub pk of 1.0 for the distribution second on the left. But letting it meander further away from the nominal specification, and the x double bar goes to 106 as it did at the process above it, we now have a C sub pk of 0, and the process is producing the same 50% relative defect product that is 50% defective, and which is the same as the process above it. Now we're going all the way over to the far right, and what you can see is even though we've got a really tight process, that is the standard deviation is 1, if we let that mean meander all the way from 100 to 109, we now have an even more negative C sub pk, and that tells us that the process is out of sight. We wanted defect-free product with lots of room for moving up and down a little bit as we head over on the far left-hand side. But now what we've got is the process is no longer centered, and it gets further and further from the center. We've got virtually 100% defective product, and we're clued into that situation by the C sub pk value of -1. I hope this particular slide, this graphic, helps to put in perspective the relationships between C sub p and C sub pk. As you can see, whether we're dealing with the top graphic or the bottom graphic, the thing that drives the capability of the process is the standard deviation. The smaller the standard deviation, the better. You've got tighter control, you've got more room to maneuver, and so if in fact the process slides a bit in either direction towards the upper or lower spec limit, you're going to continue to produce defect-free product until such time as it gets so bad that it goes outside the spec limit, and even with that tighter standard deviation, you've got a situation that demands control and investigation in the application of Six Sigma. Now on slide 18, we're still looking at those same two graphs, but I've added some words there just as a reminder. Uh, over on the far left, C sub P equals C sub PK, but only if the process average, excuse me, is exactly halfway between the upper and lower spec limits. That is, the nominal specification. Over on the far right, the C sub PK value gets smaller as the process average migrates towards either spec limit. So keep the standard deviations tight and you've got a better situation. So when that migration takes place, you've got some time, you've got some room to be able to produce defect-free product. As you can see in the upper graphic, with a larger standard deviation, in this case of 2, we almost immediately start to develop defective product. And the bottom situation where you got a much tighter control, you've got a standard deviation of 1, it takes a much longer time, and that gives you a chance to correct the situation, whatever is causing that process mean to migrate away from the nominal specification towards either of the upper or lower spec limits. Now, let's compare C sub P versus C sub PK on slide 19. Use of these indices, I believe, and I hope you believe as a result of this discussion, is important. First, using C sub P, this determines if the existing process is capable at whatever target index is desired, whether it's a C sub P of 1, 1.33, 1.67, 2, or more. Then, using C sub PK, the mean sensitive process capability index, we determine what index level the process is actually performing at for the same target index values. When the two values are equal, when C sub PK equals C sub P, we know the process is centered. This means that the lowest possible defect rate for a given C sub P has been achieved. Well, before I go into the next part of this presentation, Ashley, once again, I'll ask, are there any questions?
No questions right now.
Is everybody tuned out? There's got to be questions.
None.
I demand questions.
We have one, but it's not about the topic. It's asking about recording, so I can answer that one.
Oh, okay, fine, good. In case you folks didn't know, when I'm all finished, I'll turn it back to Ashley, and she'll answer any administrative type questions. Well, now I'm on slide 20, where it says to increase yield, increase the design tolerance, or reduce your standard deviation. So if you move your spec limits out further and further and further from the nominal spec, or you reduce the standard deviation, you automatically increase your yield, which is terrific, because the greater the yield, the greater the efficiency, the greater efficiency you have and effectiveness of the process. And you can see the plus or minus 3 sigma here, the lower control limit and the upper control limit, and you got the 99.73% area under the curve. If you go out to plus or minus 4 standard deviations, you got 99.9937% of the area under the curve. If you go out to plus or minus 5 sigma, you can see we got even more 9s. At plus or minus 6 sigma, it seems like an infinite number of 9s. And this is where the name 6 sigma comes from. If you go out 6 standard deviations, either from the nominal spec to the right or to the left, you're going from a few defects to virtually none. That is 1 part per billion, moving to the right or to the left of the process average or the nominal specification. Over on slide 21, the infamous 1.5 sigma shift, the process average, the long-term process average for the standard deviation is up at the top. And that is, you have a particular value for sigma. And at any point in time, it might be that process can be further to the right or further to the left of the target value, the nominal specification. And so you can see, for example, on Monday, let's say that's time 0, the process is centered. On Tuesday, time 1, it's moved to the right. And then it moves to the left, and then it moves to the right, and then further to the left. But when you take them all together over the week, the process tends to be centered. And so we find that as long as the process does not exceed 1.5 standard deviations, that's what we call the 1.5 sigma shift, you're in pretty good shape as far as minimizing the amount of your extent of defective product. On 22, still talking about the 1.5 sigma shift, the yield decreases when the process mean shifts from the nominal specification. As you can see where we've got in the center a process that has moved 1.5 standard deviations to the right or to the number of the defect rate changes considerably. If you've got a process that's dead center, you're going to have a 3.4 parts per million. That's ppm, 3.4 parts per million defect rate. But if you've got a process that shifts by 1.5 standard deviations, you're going to end up with like 66,803 parts per million, which is ridiculous. So you don't want to see that process mean shift more than 1.5 standard deviations. And the closer to the mean, as always, the better. On slide 23, I created this slide. God, I have no idea how many years ago. But we're now looking at Six Sigma capability and the C sub P versus C sub EK relationships. So what we've got in the center process, the center normal distribution, the shaded darkly bell-shaped curve, the C sub P equals C sub PK equals 2, and this is the process is centered. And you can see the part or process variation that exists with that particular process. But if it shifts to the right, plus 1.5 standard deviations, or to the left, minus 1.5 standard deviations, you've got some changes that have gone on. C sub P hasn't changed, but C sub PK has. In each case, it's now 1.5. So what we've got then, looking at the verbiage above the bell-shaped curves, we've got the mean where the process is centered and the distribution average is centered on the target or nominal spec. Either to the right or to the left, we've got a lower C sub PK. On the right, it's the distribution average is shifted 1.5 standard deviations to the right of the target or nominal specifications, and on the left, it is shifted in the opposite direction. And you get virtually no defects when the process has shifted 1.5 standard deviations, but you've got a 1.97 parts per billion defect rate, which is phenomenal, and that is 6 sigma. Now, talking about 6 sigma, we'll continue on here on slide 24. We're now talking about process measures. When a process is in statistical control, that is, it's both predictable and generating data that forms a normal distribution, then the following interrelationships on the next slide between the various process measures are valid equivalencies. Okay, so we've got some columns here, A, B, C, D, and F, and a row, E. Over on the right-hand side, we show how these various columns and rows relate to each other. If you take column B and column C, they always equal 1. That's the confidence level plus the significance level for a particular plus or minus sigma. So let's take what I would say is the first one plus or minus 1 sigma. You've got a confidence level, you've got a significance level, they equal 1. And in column D, that's the parts per million defect rate associated with plus or minus 1 standard deviations. And the C sub pk associated with that is listed in column F. Let's try the same thing for plus or minus 3 standard deviations. And you can see that columns B and C add to 1. The defect rate is 2,700 parts per million, and the C sub pk is equal to 1. But as you get down to 6 sigma, that's the row which we call E. Over on the far right inside that box, it says E is equal to 1.97 parts per billion. And still B and C added together are 1. The parts per million defect rate, 0.00197, which is the same as 1.97 parts per billion. The C sub pk is now up to 2. And as you would expect, as your plus or minus sigma gets higher, all the way up to 7, for example, and it can go higher than that, B and C are still the same. D has dropped down tremendously, and the C sub pk is up to 2.33. Well, this is not a table you're going to memorize. This is a table you can use as a point of reference in terms of how the product or process that you're studying, you're evaluating, is doing relative to whether you're looking at confidence level, significance level, parts per million defect rate, or the mean sensitive process capability index, C sub pk. Now, I love graphics, and across the bottom of this this particular chart, we have the parts per million defect rate, also known as DPMO, defects per million opportunities. Starting over on the far left, we've got 100,000, then 10,000, 1,000, 100, 10, and 1. Okay, so from left to right, we're going from terrible to phenomenal. And over on the far left-hand side, the column entitled Sigma, and we've got, starting at the bottom, we have 1 sigma, then 2, 3, 4, 5, 6 sigma. And in terms of grading, as in schools, 6 sigma gets a grade of A, 5 a B, a C, D, F, all the way down. Now let's, and just like with the map, we always have an arrow pointing north. You can see in orange we have the arrow pointed upwards with the tip. It happened to be at 5. It could that could just as easily have been placed somewhere else. But what we're talking about, as you can see, what the 2 sigma parts per million defect rate is, that over 300,000 parts per million, and 3 sigma, it drops down to about 67 parts per million. At 4 sigma, it drops down to 6,200. At 5 sigma, we're down to 2,233 parts per million. And at 6 sigma, we've got 3.4 parts per million. And we've given them some arbitrary names. Most processes usually start out between 2 and 3. In this case, I put the name for the 3 sigma is an ad hoc startup figure. By the time we get to 4, that's getting rid of the low-hanging fruit. That's common sense. Getting up to 5, it's no longer common sense. It's now common science. And finally, up to 6 sigma, uncommon science. So you can see there's a tremendous relationship that exists between C sub P, C sub pk, and sigma. And if you're not happy with your sigma level of your process, I highly recommend that you start evaluating the process. You drill down and find out what's the C sub P, what's the C sub pk, what's causing these things to happen. And finally, on slide 27, summary. What have we talked about? Well, we've talked about a lot of things. We talked about the normal distribution and how it's shared in the area under the curve. Offered a lot of relevant definitions. Gave you a complete example. Talked about the interrelationships between C sub P and C sub pk. And then we looked at process yield in the plus or minus 1.5 sigma shift. We looked at some process measures And finally, on that last graphic, the Six Sigma equivalencies. I hope that you feel that this has been time well spent. For some of you, it may be a review. For others, it may be information that you've never been exposed to before. Whatever the case, I hope that your time with me today, with me and Ashley, that you found that there's some new tools that you can use to help in your job in improving quality, and you've got something new to put in your toolkit. And unless there's any questions, and Ashley will let me know if there are, I'm going to turn it back to her to close out this particular webcast. Ashley, it's all yours.
Thanks, Jack. We do have a few questions that came in toward the end of the presentation, so I'll go through those now.
Okay.
The first one, does the design tolerance impact C sub P and C sub PK?
Oh, absolutely. If you go back to some of the earlier slides, the further out your design specification limits are, the greater your design specification width is. And when you divide the design specification width, that's the upper spec limit minus the lower spec limit, and then divide that value by the natural process range, the upper control limit minus the lower control limit, you're going to end up with much greater elbow room. So the greater that you can make the values of the spec limits, the fewer defects that you're going to have. Absolutely.
Okay, thank you. Could you go over confidence level versus significance level again?
Well, I didn't really cover, I mentioned what they were. Confidence level is like, in statistics, how confident are you that in the value that you've produced? And the significance level is simply the difference between the 1 and the confidence level. So if you've got a confidence level of 95%, your significance level is going to be 5%. If you're going to talk about a confidence level of 90%, your significance level is 10%. But confidence levels can be calculated very easily.
Okay, thank you. Another, in keeping with your information on page 24, is it appropriate to remind us that calculating C sub P and C sub PK is inappropriate until control charting shows that the process is in statistical control?
Absolutely.
Okay.
And that wasn't 24. I think it was 25.
Okay. Okay, great. We had a couple more come in if there's a few more minutes of time. What is the difference between C sub PK and P sub PK?
Oh, yeah. I didn't cover that at all. Before I would comment on that, I'd have to do some research on it. So I prepared for this presentation. And I know there's a difference, and I off the top of my head, I can't recall. I'd have to look it up.
Okay. One more question. What is the procedure if the process is not normal? Do I need to transform the data?
Yeah, if the process is not normal, then I guarantee you, I promise you, that what you need to do is find out what the cause of that non-normality is. If you've got a skewed distribution, skewed in either direction, if you've got a distribution that is not reproducible, if you're not able to have some kind of predictability associated with a normal distribution on whatever dimensions you may be measuring with a product, or whatever characteristics you might be looking at with regard to the process, you need to, I would say, and management would hate this, I would say you have to shut down, because you have no idea from one unit to the next whether it's going to be defective or not. And better you should shut down for a while and solve the problem and not waste a lot of raw materials than to continue to produce and not have any idea from unit to unit whether or not you're going to be able to make use of whatever is being produced in the next step of a major process, or to sell to a customer, or whatever the case may we talk about in statistical quality control and statistical process control is predicated on the assumption of normality or near normality. But if you've got skewed distributions, or it's just you're taking your life in your hands to continue operating.
Okay, thank you. We'll do one more question. We had a few more come in. Let's just do one more. If we select a confidence level of 95%, should we look at a C sub P and C sub PK of 0.67 per table in slide 25?
Okay, I've got the slide in front of me. Say that again, please.
If we select a confidence level of 95%, should we look at a C sub P of 0.67?
Yeah, that's exactly, they're equivalent.
Great. Okay, I think that covers the questions.
Let me give you just a kind of a summary on that question. Whatever confidence level, whatever plus or minus 6 sigma value you have, every item, every value in each row is equivalent. So if you went to a 98% confidence, you're talking about a C sub PK of 0.8. Let's see where I lost that. Yeah, if you were talking 99% confidence, you're talking about a C sub PK of 0.86.
Okay. All right, excellent presentation. Thank you, Jack.
My pleasure.
A few more comments before we sign off. I wanted to mention that Dr. Revell worked with the American Society for Quality to record an online series of nearly 80 webinars on essential quality tools. These are being released by ASQ for complimentary downloading by its members. Also, a recording of today's webinar will be available within a few days on the division's YouTube channel at youtube.com/ASQ Stats Division. Please be sure to share this webinar and our other archived webinars with friends, coworkers, and colleagues.
Ashley, can I add on to that?
Absolutely.
Those of you who are interested in seeing lots of the webcasts that I did for ASQ, if you go to my website, which is www.revell, spelled like my name, solution, plural.com, and then click on the tab that says webcasts, you can pick any one of those nearly 80 webcasts that are listed there on the appropriate words in the webcast listing, and at no cost, you can download. Excuse me, not download. You can view any one of those at no cost.
Great. All right. I think that's all the time we have today. Thanks everyone for joining us, and thank you again, Jack, for presenting with the Statistics Division. Hope everyone has a wonderful afternoon.
Okay, and thank you everybody, and I look forward to my next webcast with ASQ Statistics Division.